Imagine 5 people in a running race, and 3 of them will win first, second, and third. How many ways can this happen? This feels hard to count without a system because we have to think about who's first, who's second, and who's third all at the same time. So we'll write a sentence to make it more intuitive. The trick is to keep it to a single sentence with no full stops or commas. That part is important. Pretend you're the person handing out first, second, and third place, and describe what you would do in one sentence, never using a full stop or a comma anywhere in it for this to work. I will first assign someone to be in first place, and then assign someone to be in second place, and then assign someone to be in third place. Now, every time you see a phrase like "and then," you split it off into a separate stage. Here we have 2 "and then" phrases, so we split into places. Number 1, assign someone as first. Number 2, assign someone as second. Number 3, assign someone as third. Now we look at each stage and work out how many ways it can happen. The first stage has 5 ways because we're choosing first place out of 5 people. The second stage has 4 ways since only 4 people are left after we've chosen first place. The third stage has 3 ways since only 3 people are left after first and second are taken. To find how many ways the whole event can happen, we simply multiply across the stages. This is called multiplication principle. So the total is 5 times 4 times 3, which is 60. That's the long method. Now we'll cover the shorter version. It's still important to know how to write a sentence and break things into stages because sometimes you have restrictions that won't let you use the shortcut. We'll see that later in the video. Alright, let's learn the shortcut, permutations. A permutation is an ordered selection of objects from a set, and it's written NPR, which equals n factorial over n minus r factorial. N is the number of people you can choose from, and R is the number of people you choose, where order matters and there's no replacement. So in our case, n is 5 since we have 5 people to choose from, and R is 3 since we choose 3 people, where order matters and no person can be chosen twice. Substituting in, we get 5p3, which is 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial. We can rewrite 5 factorial as 5 times 4 times 3 times 2 factorial, then cancel the matching 2 factorial. That leaves 5 times 4 times 3, which is 60, exactly what we had before. Alright, exercise 1. Pause the video and try this one, and once you've finished, comment your answer below. There are 9 students in the student leader team. 1 will be chosen to give a speech, another to give an acknowledgement of country, and a third to welcome a guest speaker. How many ways can this be done? Alright, that's one part of the flowchart covered. Now let's look at another part. An old iPhone has a 4-digit PIN to log in. How many unique pins could be on there? Looking at the flowchart, order matters here, since a pin of 1, 2, 3, 4 is different from 4, 3, 2, 1, and replacement is allowed since the same number can appear more than once, like 1, 1, 2, 2. So let's write a sentence for it. I will first choose a digit for the first slot, and then I will choose a digit for the second slot, and then I will choose a digit for the third slot, and then I will choose a digit for the fourth slot. Splitting on the and then phrases gives 1. Choose a digit for the first slot, 2. Choose a digit for the second slot, 3. Choose a digit for the third slot, and 4. Choose a digit for the fourth slot. The first step has 10 ways since there are 10 different digits, 0 to 9. The second step also has 10 ways because it's still the same digits, 0 to 9. And the third and fourth steps each have 10 ways too. So multiplying across the 4 steps gives 10 times 10 times 10 times 10, which is 10 to the power of 4. That's the long way. Now let's look at the shortcut on the flowchart, n to the power of r. Here, n is the number of things we can choose from, and r is the number of things we choose, where order matters and replacement is allowed. Doing the example this way, n is 10 since there are 10 digits to choose from, and r is 4 since we choose 4 digits. So our answer is n to the power of r, which is 10 to the power of 4, just like before. Alright, now for exercise 2. Acronyms are sequences of letters that stand for a phrase. How many possible 4-letter acronyms are there? Comment your answer below. Now you know how to handle these two parts of the flowchart, both the long method and the short method. Next, let's figure out how to do them with restrictions. Imagine there are 5 friends: Abby, Betty, Cindy, Danny, and Eddie. You need to select 3 of them to volunteer at your bakery, one to do the dough, one in charge of baking, and another one for icing. But Abby and Betty recently had an argument and refused to go together. How many ways can you choose 3 friends for the job? Let's break it down. We have 5 people to choose from, and we choose 3 of them. Order matters here because Abby doing the dough and Danny baking is different from Danny doing the dough and Abby baking. And there's no replacement, since no friends can do 2 jobs at once. You might be tempted to use NPR straight off the flowchart, but we can't because NPR doesn't account for the restriction. To deal with restrictions, we write a sentence about it. Just one sentence with no commas or full stops. Think about how to avoid having Abby and Betty together. We can either just choose Abby, just choose Betty, or choose neither of them. So the sentence is, I can choose Abby and then choose 2 more friends out of Cindy, Danny, and Eddie, or I can choose Betty and then choose 2 more friends out of Cindy, Danny, and Eddie, or I can choose Cindy, Danny, and Eddie. Now let's break it up. This time we split whenever we see an or phrase. Each one starts a new case. Case 1 is I can choose Abby and then choose 2 more friends out of Cindy, Danny, and Eddie. Case 2 is I can choose Betty and then choose 2 more friends out of Cindy, Danny, and Eddie. And case 3 is I can choose Cindy, Danny, and Eddie. That looks much more doable, so let's go case by case. In case 1, we split into stages whenever we see and then. So number 1, choose Abby, and number 2, choose 2 more friends out of Cindy, Danny, and Eddie. Stage 1 has 3 ways because Abby can do the baking, the icing, or the dough. Stage 2 could be broken into more stages, but since we're just choosing 2 friends out of 3 where order matters and there's no replacement, we can use NPR. That's 3p2, which is 3 factorial over 3 minus 2 factorial, which is equal to 6. You can also just type 3p2 into your calculator to get the answer. Multiplying across the stages gives 3 times 6, which is 18. Now let's do case 2. We split into stages. Number 1, choose Betty. Number 2, choose 2 more friends out of Cindy, Danny, and Eddie. Stage 1 has 3 ways because Betty can do the baking, the icing, or the dough, and stage 2 is choosing 2 friends out of 3 where order matters and there's no replacement. So again, we use NPR, that's 3p2, which is 3 factorial over 3 minus 2 factorial, which is equal to 6 as well. Multiplying across the stages gives 3 times 6, which is 18. If you spotted the similarity earlier, you could just write 18 down straight away, since choosing Abby, then 2 more friends, has the same number of ways as choosing Betty, then 2 more friends. Alright, let's look at case 3. I can choose Cindy, Danny, and Eddie. This one could also be broken into stages, but we just have 3 friends and we're choosing all 3 where order matters. That's 3p3, which is 3 factorial over 0 factorial equal to 6 ways. You can also think of it as the number of ways Cindy, Danny, and Eddie can be arranged, which is 3 times 2 times 1. So now we have case 1 is 18 ways, case 2 is 18 ways, and case 3 is 6 ways. Across cases, we don't multiply, we add. So the total number of ways is 18 plus 18 plus 6, which is 42. There's also a faster way to solve problems like this called the complement. The idea is that instead of adding up all the counts we want, we subtract the counts we don't want. Let me show you what I mean using the same question. First, we ignore the restriction and work out how many ways we can select 3 friends. Since we're selecting 3 out of 5 where order matters and there's no replacement, we use NPR. So 5p3, which is 60 ways. But we're not allowed to have Abby and Betty together, so let's count how many ways do have Abby and Betty together, then subtract that from our 60. That sounds a bit confusing, so I'll write a sentence. First, I will assign Abby a role, and then I will assign Betty a role, and then I will choose one of the 3 friends left and give them the remaining role. Breaking it into stages, 1. Give Abby a roll. 2. Give Betty a roll. 3. Choose one of the 3 friends left for the last roll. Stage 1 has 3 ways, since Abby could be dough, baking, or icing. Stage 2 has 2 ways, since Betty only has 2 rolls left after Abby has taken one. Stage 3 has 3 ways, since there are 3 friends left to fill the remaining roll. Multiplying gives 3 times 2 times 3, which is 18 ways. Now we subtract 18 from 60 to get 42. Exactly the same answer as before, but much faster. The way you decide whether to use the complement is whether doing all the cases feels too tedious. Alright, now let's think about multi-stage events. A lottery ticket code has 3 letters where no letter can appear more than once, and 3 digits where a digit can appear more than once. How many distinct tickets can be sold? This one's a bit much at first, so let's break it into a sentence. I will first choose 3 letters, and then I will choose 3 numbers. Now into stages. 1. Choose 3 letters. 2. Choose 3 numbers. Let's work out each stage. First stage, choosing 3 letters out of our 26-letter alphabet, where no letter can appear twice, is ordered with no repetition. So we use NPR with n equal to 26 and r equal to 3. That gives 26p3, which is 15,600. Next stage. Choosing 3 numbers out of our 10 digits is ordered with repetition, so we use n to the power of r. That's 10 to the power of 3, which is 1,000. Now we multiply across stages. 15,600 times 1,000, which is 15,600,000. Great, that's our answer. Notice how we used both NPR and n to the power of r in the one question. That's what multiple stages looks like. Alright, that's it. So sometimes you have to use cases to handle a restriction. Sometimes you use the shortcuts on the flowchart, and sometimes you have multiple stages. To finish up, here are 2 practice questions that are super challenging. Give them a go. Leave your answers in the comments. Alright, now let's head over to where you can grab the notes. Alright, head to my website studeroo.com.au and make an account. From there, go to the Notes tab. And under Studeroo's notes, you'll find Permutations and Combinations, where you will have a note on counting ordered selections. That's the full set of notes for this lesson, ready for you to access anywhere you go. You can also head to the Syllabus tab and tick off the syllabus point we just covered, so you always know what you've done and what's left. If you forgot anything, you can watch the interactive video explaining it, where you can click to ask a HSC trained AI, and you can scroll down to check out the relevant HSC questions. They all come with their matching explanation video, DIY, and syllabus solution. So, what are you waiting for? Head to studeroo.com.au and start flying.